Welcome to the channel. Today, we are diving into building maintainable software architectures. Picture building a skyscraper without a blueprint. Sounds crazy, right? Yet that's exactly what many developers do when they jump into coding without thinking about architecture. In this video, we will explore how to build software that does not just work today, but stays maintainable for years to come. We will break down the solid principles, not just as theoretical concepts, but with real examples you can use in your next project. You will learn why the MVC pattern has stood the test of time, and how to use architectural views to communicate your design decisions effectively. Whether you are a student building your first large-scale application, or a seasoned developer looking to level up your architectural skills, this video will give you practical tools to build better software. And trust me, your future self and your teammates will thank you for taking the time to learn these concepts. Welcome to another lecture from the Programming Professor. Let's start with an overview of the presentation. Understanding the foundations of software architecture is key to creating robust systems. Identifying characteristics of high-quality architectures ensures scalability and sustainability. Applying solid principles leads to maintainable code and better practices. We will explore the model view controller pattern for separating concerns. Finally, we will learn how to visualize software through different architectural views. Understanding the foundations of software architecture is critical. It's the backbone of any system, providing a structure that organizes components and their relationships. Architecture serves as a mental model for developers and guides decisions in the early design phases. Good architecture is crucial for long-term success. Without it, systems suffer from ad hoc additions and increasing complexity. This leads to technical debt and difficulties in making changes. With good architecture, growth is organized, complexity is manageable, and development becomes sustainable. Solid principles serve as fundamental guidelines for creating maintainable software architectures. Each principle addresses a specific aspect of code organization. The single responsibility principle ensures each component has exactly one purpose. The open-closed principle allows systems to be extended without modifying existing code. The Liskov substitution principle guarantees that objects can be replaced by their subtypes without breaking the program. The interface segregation principle prevents classes from depending on methods they do not use. The dependency inversion principle reduces coupling by having high-level modules depend on abstractions rather than concrete implementations. Together, these principles help development teams build systems that are easier to maintain, modify, and scale as requirements change over time. The single responsibility principle states that a module should have only one reason to change. Each class should focus on a specific task, ensuring maintainability and clarity. This principle promotes modularity and reduces the complexity of future changes. Here's an example of violating this principle. The enemy class handles three responsibilities: combat logic in attack, display logic in render, and database logic in save state. Mixing these responsibilities makes the class harder to maintain and adapt. To follow this principle, responsibilities are separated into distinct classes. The enemy behavior class handles combat logic, enemy display manages rendering, and enemy storage deals with database logic. This approach improves modularity and reduces interdependence. The open-closed principle advocates for software entities to be open for extension, but closed for modification. It encourages designing systems where functionality can be added without changing existing code. Violations require modifying existing code to add functionality. In this example, the report generator class violates this principle. Adding a new report type requires modifying the generatorPort method. Each new type increases complexity and risks introducing bugs. Following this principle, we use an interface, report generator, to abstract report generation. Specific types like PDF report generator and HTML report generator implement this interface, enabling extensions without altering existing code. The Liskov substitution principle ensures that objects of a superclass can be replaced with objects of a subclass without breaking functionality. It promotes designing hierarchies where derived classes behave predictably. Violations occur when subclasses fail to uphold the behavior of their superclass. Proper implementations respect this principle, maintaining correctness. In this example, the square subclass modifies the setWidth and setHeight methods, leading to unexpected behavior. This breaks the contract established by the rectangle superclass. By introducing a shape interface, both rectangle and square implement their own behavior through getArea. This ensures that subclasses maintain predictable behavior and meet the principle's requirements. The interface segregation principle focuses on creating interfaces that are client-specific. It ensures that no class is forced to implement methods it does not use, promoting simplicity and reducing unnecessary dependencies. Large generalized interfaces lead to unused methods. This violation example shows a worker interface with unrelated methods: work, eat, and sleep. A robot class implementing this interface has to provide implementations for eat and sleep, which are irrelevant to robots. To follow this principle, the interface is split into smaller, specific ones: workable, eatable, and sleepable. Now, the robot class implements only workable, while the human class implements all necessary interfaces. The dependency inversion principle states that high-level modules should depend on abstractions, not concrete implementations. This ensures high-level modules do not depend on low-level modules, and promotes flexibility by decoupling components through the use of interfaces or abstract classes. Violations occur when code relies directly on concrete classes. In this example, the report writer class depends directly on MySQL database, a concrete implementation. This rigid dependency makes it difficult to switch to a different database without modifying the class. Following this principle, the database interface abstracts database functionality. The report writer class depends on this interface rather than a specific implementation. This enables easier swapping of database implementations. The Model View Controller (MVC) pattern is a popular design approach. It separates applications into three parts: model, view, and controller. This separation supports maintainability, scalability, and code reuse while enabling parallel development. The model component manages application data, logic, and rules. It handles storage, validation, and state management. Independent of the UI, the model encapsulates core functionality and notifies observers of state changes. For example, a student model might calculate a student's GPA as well as add and validate grades. It ensures data integrity and communicates updates to observers, keeping the application state consistent and functional. The view component focuses on the visual presentation of data. It displays information, handles UI events, and manages the interface's state. The view is tightly tied to the platform and updates in response to changes in the model. For instance, a student view might display a student's name and GPA. It provides a clear and engaging way for users to interact with the system while capturing inputs to pass to the controller. The controller component bridges the model and the view. It processes user inputs, updates the model, and selects appropriate views. This component manages the application flow and handles state transitions. In this example, a student controller might update a grade in the model and trigger the view to display the updated GPA. It mediates between components, ensuring smooth interactions throughout the system. Software architecture can be understood through various views. Code components include class diagrams, interfaces, and dependencies. These help visualize the structural relationships within the codebase. Data views focus on database schemas, entity relationships, and data dictionaries. They ensure a clear understanding of how data is stored, related, and accessed within the system. UI views include wireframes, navigation maps, and screen flows. These provide insight into the user experience and the application's interface design, helping teams plan user interactions effectively. In summary, software architecture is the foundation for system organization. Solid principles guide maintainable code design, while the MVC pattern offers a strong starting point for application structure. Visualizing different views enhances system understanding. With these principles and practices, we can build sustainable, maintainable software systems. Thanks for watching. If you enjoyed this video, please like, share, and subscribe for more lessons on computer programming and technology. See you next time.